Alright, so today we're talking about series. So remember, in the last section we talked about sequences, and I told you a sequence is different from a series in that a sequence is just a list of numbers. We were considering infinite lists of numbers. And a series is when you add together all of those numbers. Okay. So we get an infinite series or we'll just say series by adding up the terms in a sequence so the sequence AN, i.e. so we'll have A1 plus A2 plus A3 plus dot 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 plus AN plus AN minus 1, or sorry, plus 1, and so on. Right. So we have this sequence and we're just adding together all the things in the sequence. That gives us a series. And I'll say here, we use sigma notation so sigma being this letter. So we'll use sigma notation to denote series. And here sigma stands for sum. Okay. Alright, so let's write down an example here. So example, if we have the sum from n equals 1 to 4 of 3 over n. So let's write out what that means. So this is saying we're going to start at n equals 1 and we're going to add all of the terms together until we get to n equals 4. So what this means is we have 3 over when n is equal to 1, so 3 over 1 plus 3 over 2 plus 3 over 3 plus 3 over 4. Alright, so that's what that means. We're just adding together this term here for all the values of n between 1 and 4. Okay. And let's say alternatively we have the sum from I equals 1 to n of a I. Then what this means is we're going from I equals 1 to n, so we're just going to have a1 plus a2 plus dot 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 plus an minus 1 plus an. Right, so this notation just means we're adding together all of these things from I equals 1 to n. Okay, so let me use a different color here. Since we are concerned with infinite series, we'll often write the sum from I equals 1 to infinity of a I, or simply the sum of ai, right? So whenever we write this notation, we just means we're summing all the infinitely many terms of the sequence of these entries ai. Okay. So the next thing to say is the series can converge to some number, or they can diverge to infinity. Right, so those are two options, right? So whenever you add together all the terms in the sequence, you can either get that eventually you're going to come to just some number. If you add together all the infinitely many terms, you're going to either approach a number or you're just going to approach infinity, right? So those are our two options. To determine what happens, we define a sequence Sn of partial sums. Okay, so what I mean by this is, let's say we have S1, that's just going to be equal to A1, the first term in the sequence. Let's say we have S2, that's going to be adding together the first two terms of the sequence, so we're going to have A1 plus A2. If we had S3, that's going to be A1 plus A2 plus A3, and we can just keep doing this until we get, in general, Sn is going to be equal to the sum of the first n entries of the sequence, which we said we can denote this way, right? So this is just adding together the first n entries of the sequence. So I'll say here Sn is the sum of the first n terms. Okay. Alright, so next we're going to have a definition. Alright, so next we're going to have a definition. If the sequence of partial sums, Sn, so this is just each Sn is adding together the first n entries of your sequence A. So if this sequence is convergent, meaning it approaches some number, and the limit as n goes to infinity of Sn equals this number S, right? So S is just a number. So where S is a real number, then the series sum of all of these ANs is convergent and we write the sum of all of these entries is equal to S. Right, so all this is saying is if we just take the partial sums, which are these things where we're just adding together the first n terms, if this value of Sn is going to converge to some number and it converges to the number S, then we'd say the series is convergent and the sum of all the entries in the series is going to be equal to S. Okay, and the number S is called the sum of the series. Okay. And I'll say here that the sum of an, so all of the sums of the entries, is divergent if the sequence of partial sums diverges. Right. Okay, so let's look at an example. So example number 1 here. It's going to say, suppose the sum of the first n terms of the series sum from n equals 1 to infinity of an is Sn equals 2 times n over 3n plus 5. Part A is going to say find S1, S2, and S3. And part B is going to say find the sum of the series. Okay, so remember this S here is just adding together the first n terms, right? So this is the whole series just adding together all of the terms, but this Sn is just part of it where you're adding together the first n terms. Okay. So the first part says we need to calculate S1, S2, and S3. Right, so this is just as simple as plugging numbers in. So S1, so for part A, we're going to say S1. We already have a formula for this, so we're just going to plug in the numbers. So it's going to be 2 times 1 over 3 times 1 plus 5. Right, so if we just plug in the numbers, this is what we get, which is 2 over 5. Or sorry, 2 over 8. Which is 1/4. Okay. And then S2, we do the same thing, we just plug in 2. So we get 2 times 2 over 3 times 2 plus 5, which is, so that's 4 over 11. And then now just we have S3, which is going to be 2 times 3 over 3 times 3 plus 5, so that's 6 over 9 plus 5 is 14, so 6 over 14, and if we simplify that, we can divide with the numerator and denominator by 2, so we get 3 over 7. Right, okay. So for part B, we need to find the sum of the series. The sum of the series is equal, so you can pause here and think about how are we going to find the entire thing, this entire series here, how are we going to find that given this equation? And the answer here is the sum of the series is equal to the limit of the sequence S n. So if we just write that, so we said the sum from n equals 1 to infinity of an, we said that's the limit as n goes to infinity of Sn, right? Because Sn is just adding together the first n terms. If you're going to take the limit as n goes to infinity, then this is adding together all infinitely many terms. So this is exactly what we have here. And now we actually have a formula for Sn, so we could just plug that in. Just limit as n goes to infinity of what we said our formula was, which was 2n over 3n plus 5. Right. Now we need to go back to Calc 1 and remember how to take a limit like this. And remember our strategy for these types of limits was always to divide by the highest power of n in the denominator. So the highest power is just n, so we divide both the numerator and the denominator by n. So if we divide both the numerator and denominator by n, then we're going to have the limit as n goes to infinity of, so divide the numerator, you get 2. Divide the denominator, you get 3 plus 5 over n. Right. So I just divided both of these, the numerator and the denominator, by n. This is what we get. And if n is going to infinity, then 5 over n, that's certainly going to 0. So this part goes away, and you're just left with 2/3. So that would be our answer. So if we add together all the infinitely many terms in our series, we're going to be approaching the number 2 over 3. So we're going to say that that's the sum of the series. Okay. So let's do another example here. Let me just flip to the other side here. So let's do number 2. It's going to say, show that the sum from n equals 1 to infinity of 1 over n times n plus 1 is convergent. Okay, so that's our goal. Remember, in the last problem, they actually gave us a formula for Sn, the partial sums, right? If you add together the first n terms, they gave us a formula for how to do that, but we don't have that here, so we're going to have to figure that out. So, write down in words what I said just there. So note, in example 1, we were given a formula for Sn. Here we need to find one ourselves. Okay, so that's what we need to do. So if you remember Sn, we said that that's the same thing as adding together the first n terms. So I equals 1 to n of 1 over I times I plus 1. Right, so Sn is the same thing as the sum. The sum is just adding together the first n terms. And now we just need to write this out. So this is, if you plug in 1, you get 1 over 1 times 1 plus 1, which is 2, plus, if you plug in 2, you get 1 over 2 times 3. If you plug in 3, you're going to get 1 over 3 times 4. And you just keep going until the nth term. If you plug in n, you're going to get 1 over n times n plus 1. Right, so this is our formula. This is what we get. Okay. So now we can say, so this is just the same thing, and note that one over I times I plus 1. Remember, whenever we were learning about partial fraction decomposition, we can actually decompose this. So we can write this as A over I plus B over I plus 1. Right, that's just partial fraction decomposition. Okay. And remember what we did in partial fraction decomposition. We set the left numerator, 1, equal to whatever we get on the right side, which for the first term is going to be whatever you need to multiply this fraction by on both sides to get the denominator to match, right? So notice here the denominator is I. This is I times I plus 1. So we need to multiply both sides by I plus 1. So the numerator is going to be A times I plus 1. And same thing here. We need to multiply both sides by I. So the numerator on the second fraction is going to be B times I. Right. Okay, so we actually get this equation just relating our numerators. Now we can go ahead and, well, let's just go ahead and write out what this is equal to. This is 1 equals A plus B times I plus A. Okay. Now notice this thing in front of I should be 0 because on the left side we don't have an I. So this thing here is 0, and this thing here should better be 1, right? So A is 1, so we get the A equals 1. And if A is 1, and if you add A and B you get 0, then you're going to have to get that B is negative 1, right? Because A plus B then needs to add to give us 0. Right, so that's just from solving the two equations, A plus B equals 0 and A equals 1. Right. Okay, so now we can actually rewrite this. So we can rewrite, so 1 over I times I plus 1 is equal to, so we said A was 1, so 1 over I minus 1 over I plus 1. Okay, so we can break it up like that. So let me write over here. Then Sn equals the sum from I equals 1 to n of 1 over I minus 1 over I plus 1. Right, and the same thing I did up here was I just wrote out what this looks like. I'm just going to write out what this looks like. So if you write it out, then plug in 1, you're going to get 1 over 1 minus 1 over 2. Plus, if you plug in 2, you're going to get 1 over 2 minus 1 over 3. If you plug in 3, you're going to get 1 over 3 minus 1 over 4. And you just keep going. And then if you plug in n, you're going to get plus 1 over n minus 1 over n plus 1. Right. Okay, so the reason I wrote this out is we just need to look at this and see if we can cancel anything out. Well, 1/2 minus 1/2, that cancels out. 1/3 minus 1/3, that also cancels out. And here we're going to get a 4th minus a 4th, that's going to cancel out. So all these things are going to cancel out, except, so we're going to have minus 1 over n, and then we're going to have plus 1 over n, so that cancels out. And what you're left with is just the first term and the last term. So you're going to get 1 minus 1 over n plus 1, because all the other stuff is going to cancel out. Okay, so what we get here is that this is actually equal to 1 minus 1 over n plus 1. So we actually have a formula. This was Sn. So Sn, we actually have a formula for it. So that was the hard work of figuring out what our formula was, right? Last time they gave us the formula, we had to figure out what this formula is for adding the first n terms of our sequence. Whenever we do that, that's what we're going to get. Okay. Now, so the sum from n equals 1 to infinity of an equals the limit as n goes to infinity of Sn. But we already have a formula for Sn, so it's the limit as n goes to infinity of 1 minus 1 over n plus 1. And now we can actually just compute this limit, right? So we just try plugging in infinity. We get 1 minus 1 over infinity. Well, 1 over an infinitely big number, that goes to 0. So we're just going to get 1, because this fraction is going to go towards 0 as n gets infinitely big. Okay, so what we can say here is, so the sum of all of these entries in the sequence is convergent, and its sum is actually equal to 1, right? So if you add all the infinitely many terms in this sequence, you're actually going to get 1. Okay. And I'll say here, notice in example 2 how our terms cancel it out in pairs. We actually have a name for this. This is called a telescoping sum. Right, so whenever you get things canceling out in pairs like that, we're going to call that a telescoping sum. I'm going to erase the next board here. So we saw in example 2 that finding Sn can be tedious. So we want tricks and tests to see if our series converge or diverge. Right, so we want to develop some tools in order to see whether our series converge or diverge, because we saw here figuring out what Sn is actually equal to was kind of difficult. Okay. And I'll say here secondly that many of these tricks only work for certain types. A series, using them requires us to recognize the type. Right, so you just have to be a little bit careful when you're using these techniques, because these are only going to work for certain types of series. So the first type of series that we're going to talk about is the geometric series. Okay, so a geometric series has the form so it's going to look like the sum from I equals 1, sorry, from n equals 1, sorry, I meant to write here, from n equals 1 to infinity of a times r to the n minus 1. Right, so if you see something that looks like this, we call it a geometric series. And if we write out exactly what this means for each value of n, so if we plug in n equals 1, so r to the 1 minus 1, r to the 0 is just 1. So we're going to get a plus we're going to get a times r if we plug in n equals 2 plus a times r squared plus a times r cubed, and then this is just going to keep going, right? So this is what our series is, where a is not equal to 0. Okay, so we need to figure out when we actually have a geometric series, and I'll say here, you can recognize a geometric series by checking if multiplying each term by a common ratio r always gives the next term. So what I mean by that is you have your first term. If you multiply this by r, you get your second term. If you multiply this by r, you get your third term. Multiply this by r, you get your fourth term, and so on, right? So let's write down an example. Alright, so if we have an example here, if we have 1 plus 1/2 plus 1/4 plus 1/8 and so on, right? So we're just given this sum and we're trying to figure out how to write this as a geometric series. Well, notice to get from this term to this term, what do you have to multiply this by? Well, you have to multiply this by 1/2 to get to here. To get from this term to this term, you just multiply it by 1/2. To get from this term to this term, you just multiply it by 1/2 again, right? So a geometric series is just one where to get to each next term, you're multiplying it by the same number, right? So you multiply it by 1/2, 1/2, 1/2, and so on, right? So the next term you can guess what the next term is going to be because you can just multiply this by 1/2, that's your next term. So that's going to be 1/16, 1/32, and so on. Okay. So we can ask for a question, what is A and what is R, right? So if you look at the formula, the first term should actually be A. So this first term is A. So here, A is our first term, 1. And that R we said was our common ratio that we're multiplying everything by. And we said to get to every next term, you multiply by 1/2. So we're going to have that r equals 1/2. Okay. So that tells us what we need to know. So this is a bit of a, so just to set us up for our next result, I'm going to say something. Observe that Sn equals a plus a times r plus a times r squared plus dot 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 plus a times r to the n minus 1. So if we have r times Sn, right, this is a bit poorly written, but r times Sn is going to be equal to, so if we just multiply this whole thing by r, then we're going to get a times r plus a times r squared plus a times r cubed, and so on, until we get to a times r to the n, right? Because this was r to the n minus 1, we multiply by r, that's what we got. Okay, so subtracting, what we're going to get is going to be that Sn minus r times Sn is going to be equal to, so if we do this, we're going to have a plus ar plus a r squared plus dot 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 plus a times r to the n minus 1 plus, or sorry, minus. So we're subtracting whenever we have this one here. So this thing here, we're subtracting it. So ar plus ar squared plus ar cubed plus dot 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 plus a r to the n minus 1 plus a r to the n. Right, so we're subtracting off that. And now, if you notice, we can just pair together each of these terms. Right, so ar also appears over here. So we've got ar minus ar, that cancels. Ar squared minus ar squared, that cancels. And all of these, so this one also cancels with this. So all of these are going to cancel out. Right? So each of these terms cancels out with each of these terms, except we're still left over with this one on the end, a times r to the n. Right? So in the end, we actually only have two terms left. So this is going to be equal to a minus a r to the n. Okay? So the whole goal was to solve for Sn here, and now we actually see we can actually solve this for Sn because we have this side is equal to this. So we have Sn minus r times Sn is equal to this right side here, and now we can just solve for Sn because we can factor out Sn here. Sn times 1 minus r equals a minus a r to the n. And now we divide both sides by 1 minus r, so Sn equals a minus a r to the n over 1 minus r. So we've solved, whenever we have a geometric series, that's the assumption we started with, whenever we have this geometric series, we solved exactly for what Sn has to be equal to. But what we actually care about is the limit as n goes to infinity of Sn. Right? Because we care about, if we add together all of the sums in this, all the entries in the series, we care about what that's equal to. So we want to figure out what this is equal to. So this is the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r. And let's go ahead and assume, let me write down here, assume that negative 1 is less than r is less than 1. So we're going to make that assumption. Then we need to look at what's happening here. So n is going to infinity, and we've got this relatively small value of r. So if we keep multiplying that by itself, this thing, what is this thing going to go to? What does r to the n go to if, let's say, r is equal to a half, and you keep multiplying a half by itself? Well, if you just keep multiplying a half by itself, this is going to 0, right? Because 1 half times 1 half times 1 half times 1 half, the more you do it, the closer and closer you get to 0. So this part is going to 0 if we have that assumption. This is the important assumption here. So if we have that assumption, that part goes to 0. So we're going to get a over 1 minus r. Okay, so this whole thing that I did here was just to say, whenever you have a geometric series, and we have that r is between these numbers, then if we add together all the terms of the series, we have a nice formula to figure out exactly what it's equal to. So I'm just going to go ahead and state that in a theorem. That was the whole goal, to figure out. So theorem number 1 is going to say the geometric series so it's the sum from n equals 1 to infinity of a times r to the n minus 1 is convergent if the absolute value of r is strictly less than 1 and has some a over 1 minus r if absolute value of r is greater than or equal to 1, then the series diverges. Right. So remember what I said earlier, first we've got to figure out what type of series we have, but if we do have a geometric series that looks like this, then we actually have a very nice way of figuring out whether it converges or diverges. If the common ratio here is greater than or equal to 1, it diverges, it goes off to infinity. If the common ratio is strictly less than 1, then if you add together all of the terms in the sequence, you're going to have that your answer is going to be that. So it's going to be a over 1 minus r. So let's just use this in an example. Find the sum of the geometric series and our series is going to be 3 minus 2 plus 4 over 3 minus 8 over 9 plus dot dot dot. Right. So remember this is an infinite series, so it's just going to go on forever. And if it says in the beginning that we're working with a geometric series, so we've got to figure out a and r. Those are our two things that we care about. So remember what I said here, whenever we're looking at this geometric series, our first term is always a. So we can already figure out what a is equal to. So I'll say here in blue, we need to find a and r, and we said here that a is equal to 3. And remember what I said, the common ratio, r, whenever we have one term to get to the next term, we need to multiply by the common ratio. So putting that in math terms, r is always going to be equal to ai plus 1 over ai. Right? It's the ratio between the next term and the previous term. So it's just take this term divided by the previous term, that's going to give you the common ratio. So for example, r equals, so we said whenever we have ai plus 1 over ai, so we'll just let I equal to 1, so a2 over a1. Right, so if you just pick two consecutive terms to do this with, then you're always going to get the same answer. So let's just take the second term over the first term. So that's negative 2 over 3. So that tells us to get to each next term, we multiply by negative 2 over 3. So this times negative 2 over 3 gives us negative 2. This times negative 2 over 3 gives us this. This times negative 2 over 3 gives us this, and so on. Right, so we've found our common ratio. Okay, so since the absolute value of r equals the absolute value of negative 2/3 equals, or sorry, is less than 1, the sum is, so what can we do here? Well, it says here if the absolute value of r is less than 1, then we can use this theorem. And it's going to say that this has this sum. So the sum is a over 1 minus r, and we just plug in what we know. So a is 3, and 1 minus, we said r was negative 2/3. Right? So we just plug all this information in. We're going to get 3 over 5/3, which is going to be 9/5. Right? So if you add together all of these infinitely many terms, eventually what you're going to get to is going to be 9/5. That's going to be your final answer. Right? So if I just give you the sequence, it looks like, well, how the heck, the series is what I meant to say. How the heck am I supposed to actually figure out what this is equal to? Well, we just need to use this theorem, right? So we just use the theorem, and it gives us the answer. Okay. So we don't always know whether something is actually a geometric series. So in that problem, they just told us that it's a geometric series. But we don't always necessarily know that, so we need to sometimes figure that out. So that's going to be the next example here. So sometimes geometric series can be distinguished and our example here, example number 4, is going to say, is the series so it's the sum from n equals 1 to infinity of 2 to the power of 2n times 3 to the power of 1 minus n convergent or divergent. Right. So a little bit hard to read here, but this is 2 to the power of 2n and 3 to the power of 1 minus n. And we're asking if the series is convergent or divergent. So if it is actually a geometric series, that would actually be very useful information because we can just use the theorem. So that's what we've got to figure out. So I'll say here the series is geometric if we can write two to the power of 2n times 3 to the 1 minus n in the form a times r to the n minus 1. Right, so if we can somehow rearrange this into this form, then we're going to get that the series is actually geometric. So that's our goal. So let me write down here an equals, so we had our 2 to the 2n times 3 to the 1 minus n. And we want to get these powers closer to each other. So one thing I can do is say that this is the same thing as 2 squared to the power of n, right? 2 to the power of 2 and then to the power of n. You can multiply the powers to get back to here. So I can just separate it, and now this n looks much closer to this 1 minus n. So we can rewrite this next part as 3 to the negative 1 to the power of n minus 1. Right, so I wanted to get this n minus 1, and the way I'm doing it is by first multiplying this by negative 1 and bringing it here. Because now if you multiply these two numbers, you get back to the power that you started with. So I'm just cleverly rearranging things a little bit. And now what we notice is this is equal to 4 to the power of n times 1 over 3 to the power of n minus 1. Okay. And now we can say, well, we actually want this to be an n minus 1, not an n. So what I'm going to do here is break this apart as 4 times 4 to the n minus 1, right? Because this is n minus 1 copies of 4. This is 1 copy of 4. If you multiply them together, you get back to n copies of 4. So I just broke it up a little bit. Times 1 over 3 to the n minus 1. And now we've got the same power in different bases, different numbers here. So if I've got 4 to this power times 1/3 to this power, I can actually just bring the 4 on the inside. Right? So what I can do here is actually say that this is equal to 4 times 4/3 to the power of n minus 1. And now we look at this, and we look at this, and we'd say, well, a times r to the n minus 1, that's exactly the form that we have here. So that's what we wanted. So now the sum from n equals 1 to infinity of 2 to the power of 2n times 3 to the power of n minus 1 is actually equal to the sum of 4 times 4/3 to the n minus 1. So we can figure out what our values of a and r are. So a equals 4 and r equals 4/3. Okay, and now we look at our value of r, and we look at our theorem, and we say, well, the absolute value of r, here the absolute value of this is 4/3, the absolute value of r is greater than 1, so the series diverges. So that theorem actually just tells us immediately that this series is going to diverge. So I'll say here, since absolute value of r is strictly bigger than 1, by theorem 1, the series diverges. Right, so you can see from this example, sometimes you have to do a little bit of work to rewrite this in this form in order to say, well, yes, this is actually a geometric series, and then once you figure out the value of r, you can just figure out what to do by looking at this theorem. It's a very important theorem. Okay, and the next thing to note So the next thing to say is that we have a name for the following series, so the harmonic series. So we'll call this the harmonic series whenever we have the sum from n equals 1 to infinity of 1 over n, which if you write out what this is just 1 over 1, which is 1, plus 1/2, plus 1/3, plus 1/4, plus 1/5, and so on, right? You can just keep writing out terms. There's infinitely many terms. So this is called the harmonic series, and I'll write here extremely important fact. So an extremely important fact here is the harmonic series is divergent. Right. Okay, So we want to actually prove this. So I'll write here proof sketch. So I'll say here we will look at S2, S4, S8, S16, and so on. So we'll just look at the powers of 2 and adding together. This is adding together the first 2 terms, adding together the first 4 terms, and so on. So let's just add together the first 2 terms. So S2 is going to be equal to, this would be 1 plus 1 over 2. The next thing is S4. So if we add together the first 4 terms, we've got 1 plus 1/2 plus 1/3 plus 1/4. And we can write here, well, this part here is greater than 1/4. So this is actually greater than 1 plus 1/2 plus 1/4 plus 1/4, which is actually going to be equal to 1 plus 2 over 2. Okay, so we just do this next with S8. And we're going to get, so this would be 1 plus, so I'm just going to write out all the terms. Okay, so if we write out all the terms, that's what we get. And I'll write here that, let me just use a different color. So this part here, this is greater than 1/2. And this part, for each of these are each greater than 1/8. So if we add all these things together, what we're going to get is going to be that this is greater than 1 plus 1/2 plus 1/2 plus, now if we add together 1/8 4 times, we're also going to get 1/2, which is going to be 1, sorry, that's not what I want to write. 1 plus 3 over 2. Right, so you can kind of see a pattern that's starting to develop. So I'll just do one more here. So S16 equals, so we're going to have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus, and I'm just going to write some dots here, plus 1/8 plus 1/9 plus, and I'm going to write some more dots here, plus the 16th. Okay, and now we're going to do a little bit of grouping, and we're going to say that this part here is greater than 1/2, and this part here is going to be greater than 1/2, and this part here is also going to be greater than 1/2. So if we just add all those things up, then this thing is going to be greater than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, and if you add all those things together, you're going to get 1 plus 4 over 2, right? And we're just going to keep doing this. So I'm not going to write out all the steps because we've already written out quite a few steps here. Let me erase this. So the next thing here would be S32, which is going to be greater than 1 plus 5 over 2. S64, which is going to be greater than 1 plus 6 over 2. And in general, you're going to get S2 to the n, which is going to be greater than 1 plus n over 2. Okay, so if we add together the first 2 to the n terms, we're going to get a number that's bigger than this. So now we want to take the limit as n goes to infinity of s to n, 2 to the power of n, right? So this is just saying we're taking the limit as we eventually add together all of the infinitely many terms. So this is going to be equal to, so we already have an expression for that, or sorry, this is greater than is what I meant to write. It's greater than or equal to the limit as n goes to infinity of 1 plus n over 2. And now we can take this limit and say that this is actually, if n is going to infinity, then this thing on the inside here is also going to infinity. So this is infinity, right? So it turns out our answer is infinity. So if we add together all these terms, our answer is actually going to be infinity. That's what all that work showed. So since s2 to the n goes towards infinity as n goes towards infinity, so does Sn. So the sum of 1 over n diverges. Right, so all this work was just to show that this sum, if you add together all these numbers, you're going to go towards infinity. Okay, so just restating, the important fact here is that this harmonic series is divergent, and let's write down the next theorem. Okay, so theorem number 2 is going to say if the series sum from n equals 1 to infinity of an is convergent, then the limit as n goes to infinity of an is equal to 0. Now, this is a very attractive looking theorem because it looks like, well, if we just take the limit of our sequence, if it's 0, then it's convergent. If it's not 0, then it's not convergent. But that's actually not saying exactly what this theorem is saying. You have to be a little bit more careful than that. So that's actually a wrong statement, what I just said. Because what this is saying is, if this is convergent, then this limit is equal to 0. So it just having this limit is equal to 0 isn't enough to say that it's convergent, but if this limit is not equal to 0, we can definitely say that it's not convergent. So you just have to be a little bit careful there, because just proving that this is 0 is not enough. But if you prove that this is not 0, then it will say that it's not convergent. So you just have to be a little bit careful with exactly what that theorem says. So I'll write here the converse of theorem 2 is not true with an exclamation mark, i.e. if the limit as n goes to infinity of an is equal to 0, it is not necessarily true that the sum of all these guys converges. For example, so an equals 1 over n. So that goes towards 0 as n goes to infinity. But we saw here that the sum of all these entries is actually not going to be equal to a number. It's divergent. It's infinite. So, but the harmonic series the sum 1 over n is divergent. Okay, so you just have to be pretty careful there, because you can say one direction if this holds, then this holds, but if this holds, then the first statement doesn't necessarily hold. Okay, so let's say here test for divergence. So the way we can test if something is divergent, and I'll say that this is the contrapositive of theorem 2. So contrapositive is just a logic word, but what I mean here is if A implies B, then not B always implies not A. So I'm going to negate the second statement, and it's going to imply the negation of the first statement. So what that means in words is if the limit as n goes to infinity of an does not exist, or the limit as n goes to infinity of an is not equal to 0, so that's the negation of this statement, then the negation of the first statement holds. So then the series, the sum from n equals 1 to infinity of an is not convergent, but not convergent means is divergent. Right, so these two theorems are actually saying, or these two statements are actually saying the same thing. It's just that this second statement is first negating the second thing here, and then saying that that implies the negation of the first thing. Okay. So if your limit does not exist or is non-zero, then your series is divergent. So this is actually quite useful still. So in general, we can see if its series diverges by finding the limit as n goes to infinity of an, and if it doesn't exist or it's non-zero, then it's divergent. Okay, so example number 6, or sorry, example number 5 is going to say, show that the sum from n equals 1 to infinity of 3 n cubed over 5 n cubed plus 4 n squared minus 4 diverges. Right, so if we're trying to prove that something's divergent, we want to use this here, the divergence test. So we want to prove we need, let's use a different color. we need to show that the limit as n goes to infinity of 3n cubed over 5n cubed plus 4n squared minus 4 either does not exist or is not 0. Okay, so now we can just try to find this limit. So the limit as n goes to infinity of this fraction 3n cubed over 5n cubed plus 4n squared minus 4. So we need to just find this limit. And if n is going towards infinity, remember what we're doing, or just for any limit like this, remember what we're doing, so since n is going to infinity, we need to divide by both the numerator and the denominator by the highest power of n in the denominator. So divide both sides by n cubed. So if we do that, we're going to have 3, limit as n goes to infinity, of 3 over 5 plus 4 over n minus 4 over n squared. Right, so I just divided both the numerator and denominator by n cubed, and now if n is going towards infinity, both of these fractions are going to 0, so our answer is 3 over 5. And you can check, 3 over 5 is not 0, so by what I wrote up here, we're saying since our limit is non-zero, then the series is divergent. So we're just going to say here, since the limit is non-zero, the series diverges. Right, so that's how we figure out if a series is divergent. Okay. Now, let's write down some properties that we can actually use for these problems. This needs to be adjusted. There we go. Okay, so as I said here, we need to write down some properties. So properties of convergent series. If the sum from n equals 1 to infinity of an and the sum from n equals 1 to infinity of bn are a convergent series, then so are the series. So part A is going to say the sum from n equals 1 to infinity of c times an, which is the same thing as c times the sum from n equals 1 to infinity of an, where c is a constant. Right, so if we have a convergent series, if we just multiply each term by some constant, then we're still going to have a convergent series. All right, part B is going to say if we have the sum from n equals 1 to infinity of an plus or minus bn, right, so we're taking, let's say, the nth entry in an, and we're going to add or subtract the nth entry in bn. If we do that for all of the terms, then actually what we're going to get is going to be the sum from n equals 1 to infinity of an plus or minus the sum from n equals 1 to infinity of bn. But since we said each of these are convergent series, then this is just some number, and this is some number. So overall, this is just some number, so it's a convergent series. Okay, so let's now write down our final example. So example number 6 says, find the sum of the series sum from n equals 1 to infinity of 3 over n times n plus 1 plus 1 over 5 to the power of n. Okay, so let's just write down what we have here. We're given sum from n equals 1 to infinity of 3 over n times n plus 1 minus 1 over 5 to the n. But remember what I said here, we can just break that into two sums. So we can break that apart as the sum from n equals 1 to infinity of 3, and we can factor out constants. That's the other thing I meant to say. So we can factor out our 3, so it's 3 times the sum of 1 over n times n plus 1 minus the sum from n equals 1 to infinity of 1 over 5 to the power of n. Okay. So let's just go ahead and look at this. This first series here, we actually already solved what this is equal to. So I'll say we solved this in example 2. So we solved that one in example 2. So we actually already know what that's equal to. And so we said that was equal to 1. So we already know that. And I'll say here that this is a geometric series. Right, your clue to whether it's a geometric series is whether you have something raised to the power of n. So that looks like it. So it's probably going to be a geometric series, and it turns out it is. So it's a geometric series. And you've got to figure out what your values of a and r are going to be, right? So a, remember, was the first term of the series. So if n equals 1, then your first term is going to be 1/5. So a is the first term, 1/5. And then you've got to figure out r. What are you multiplying each term by to get to this next term? So if we just write out what this is equal to, our first term was 1/5. Our second term, if we have n equals 2, is 1 over 5 squared. Our third term is 1 over 5 cubed, and so on. Right? But to get to each next term, notice you're multiplying by 1/5. So r is actually also 1/5. Because the common ratio to get to one term to the next term is going to be 1/5. Okay. And remember, for a geometric series, our answer for what the series is actually equal to was a over 1 minus r, as long as this number, the absolute value of this number, is less than 1, which it is. So this is going to be our answer for this sum. So we can just plug in what we know. So if we plug in what we know, this is going to be equal to 3 times, we said in example 2 that this was 1, minus, we just had to plug in a and r. So it's 1/5 over 1 minus 1/5. Okay. And now we just solve this. This is 3 plus 1 over 4, which is going to end up being 13 over 4. So this is actually our final answer. So this sum is actually just equal to 13 over 4. If you add together all infinitely many numbers here, you're going to get 13 over 4. Okay. Let's just write down one more thing. Okay, so a final note. Suppose we show that the sum from n equals 40 to infinity of n over n cubed plus 1 converges. Then we know that, so this would be the sum from n equals 1 to infinity of n over n cubed plus 1 converges. Right, so notice the difference between these two expressions. This is just starting at the 40th term of the sequence, and this is actually starting at the first term. Right, this is starting at n equals 1, this is starting at the 40th term. But if we start at the 40th term and we add all of the terms after that, then, well, if we just add in 40 more terms, that's still going to be a finite number. Right, so this is a finite number. We add 40 more terms, it's definitely still going to be a finite number. So this converges since the sum from 1 to infinity of n equals 1 to infinity of an equals the sum from n equals 1 to 39 of an plus the sum from n equals 40 to infinity of an. And notice here, this here, let me use a different color. This is a convergent infinite series, and this here is just some finite number. Right, this is a finite sum, so it's going to be a finite number. So we can just say, whenever we have something like this, we can just change the bottom limit to be n equals 1. So our rule here is going to be the sum from n equals 1 to infinity of an converges if and only if the sum from n equals capital N to infinity of an converges for capital N greater than 1, right? And here I'll just note that if and only if means if you have the first thing here, then you have the second thing, and if you have the second thing, you also have the first thing, right? So if you satisfy the first condition, you satisfy the second. If you satisfy the second condition, you satisfy the first. That's what if and only if means. So what this is saying is, if you just start at, let's say, the millionth term of the sequence and you add everything after that, if that's some finite number, then it turns out if you just add in the first however many terms, you're still going to have a finite number, right? So this is what that's saying. And just as one final note, you might encounter this in the homework. If you have something that looks like n with an exclamation mark next to it in the homework, then this actually means n factorial, which is the same thing as saying n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So all n factorial means is you multiply all of the numbers that are less than n, all the integers that are less than n. So n times n minus 1 times n minus 2 and so on. You just multiply everything that's less than or equal to n together, and that's n factorial. Okay.